All right, let's do some torque problems with rolling because this is going to be a little bit tricky and it's going to be on the exam. So I want to make sure that I actually have this set up for you. So we have a rolling with slipping problem, and what that means is you have something that's rolling on the ground. Well, it's spinning on the ground and it can't seem to get some grip to get rolling. So it's spinning in place is how I would describe it. So to this end, let's just go ahead and get our problem set up. So for part A, first of all, let's just get a free body diagram drawn. Free body diagram. I cannot talk. Free body diagram. Sorry, that's a bit weird. All right, here we go. We got a normal force. We got a weight. We got a friction force on the ground here. And the velocity, the center, is right there. So let's be clear here. Initial velocity of the ball is the same as the center of it. And as we begin the problem, here's what it says. So throwing the ball, coefficient of friction. So it is rolling smoothly. So to start with, what we're saying is, let's get to the point now where we're rolling without slipping. That part is straightforward and pretty easy in that there we're just going to say V over R is what that is. So basically V center mass is just going to equal omega times R, whatever that is. Now for B, we now have that the ball is sliding, and we want to know its linear acceleration and its angular acceleration. So let's kind of be clear. So for the linear acceleration, we have friction simply slowing it down. It's basically trying to sort of slide in place, and all that's happening here is, it's slowing a little bit. It's got a little bit of sliding going on, and so here we're going to basically say that mu mg equals ma of the center mass. That cancels, so a center mass is going to equal negative mu times g. Now for the angular acceleration, what's happening there is that we have the same friction applying a torque. And so we can basically say mu mg equals 2/5 mr squared times alpha. But we're not going to assume that alpha is a over r in this case because we're sliding. So this will cancel. And so we're going to end up getting 5/2 mu g over r squared equals alpha. Let me make sure I have that right. Mu mg. The friction applies a torque. So this is the force of friction, and we have to multiply it by the lever arm. Sorry about that. So there's an r here, and that cancels with there. So our alpha ends up being mu g over r times 5/2. That's the alpha. Now, let's just kind of continue here. If we have part D, on this page is where we'll continue D. So here's what we'll say. We know that V center mass equals V naught plus A center mass times T. And then we have the rolling acceleration, which is alpha times T rolling. So let's just do a little ratio here. We know V over omega equals R, the radius. So we can say V naught plus AT equals alpha times T. And that equals the radius. So what we want to do is we want to actually end up isolating T. Now, I'll let you do the algebra on this, but it turns out when you isolate T, it ends up being V naught over A rolling plus A center mass times R times alpha, which we calculated above, which ends up being like 8.5 divided by 2.06 plus 0.11 times whatever we got for alpha. Anyway, I'll let you figure that out on your own, but that's the way to set it up. Now for E, It's basic kinematics. X is v naught t plus 1/2 a t squared. And you're going to use a center mass, and same with the v equals a t plus v naught. So I'll let you figure those two out. So that's it for that part right there. So that is that's the second problem.